This conference will
There we
now
go.
be recorded.
Okay, so we are on record. Good morning, everyone. Good afternoon. For today's session, we're going to start off with Macinkowski, sorry, from Intel, who will be presenting
Machnikowski, yeah.
Macinkowski, sorry, from Intel, and the main topic for their presentation is going to be PTP4L, and we're going to use the remainder of the time to discuss the other work streams and affairs at TAP. So unless there's anything else to raise, we'll kick it off and over to you, Maciej.
Okay, so let's start. I am Maciek Machnikowski. I work for Intel. I'm a tech leader at EPG Software, and I'm currently handling everything that is related to time on our networking cards. And I'm here to briefly introduce the PTP, starting from the brief introduction to the protocol and then the whole Linux stack that we need to enable to actually get it up and running. So first, the word from our sponsor. And now I'll briefly introduce the agenda. So first, I'm gonna introduce the PTP itself, give a brief overview of the PTP protocol, and talk a little bit about types of timestamping and errors in the protocol. Then I'm going to talk about the kernel interfaces, about the sysfs, about the if tool output and where to look to actually debug the NIC support. And in the end, I will introduce the Linux PTP toolkit, which is actually the set of tools that we use to control and to enable PTP in our products. So let's start with the brief PTP overview. I'll try to breeze through this because I assume that most people in this forum are aware of what PTP is.
Yeah, I think we have a good level of understanding by now.
Yeah. So it's a precision time protocol, IEEE 1588 standard, can synchronize timers to sub-microsecond accuracy. It's a hierarchical master subordinate architecture for the distribution of clocks, provides the administration-free operation, and is good for both high-end and low-end devices. It's generally considered better than NTP and worse than GPS, so it's where it's positioned. A couple initial definitions. Grandmaster clock is the ultimate source of time for the synchronization using the protocol within the domain that we're trying to synchronize. It's usually implemented as a clock that is synchronized to a very accurate source of time, such as the GPS module or other stable source. Ordinary clock is a clock that has a single PTP port in our domain. It can be either master clock or a subordinate clock that synchronizes to another clock. And then there is a boundary clock, which is a clock that has multiple PTP ports. And usually one of those ports is synchronized to another master, and other ports serve as masters to a given subdomain. Then the master clock is the clock that we use as a source of time, and the slave or subordinate clock is the one that we are synchronizing to the master. And PHC is the PTP hardware clock. This is a dedicated hardware component on our NIC that is used as a time source and is actually the timer that is synchronized by the PTP protocol. And yeah, to quickly illustrate this, in our simple PTP network, we can have a grandmaster clock, which is, as we can see, I don't know if the cursor is visible. Probably
Yeah,
not.
we can see the cursor. Hey,
Okay, there
Matt,
is also
JD,
a, yeah.
I would like to set the discussion into the areas where Intel is doing the recent developments and where you want to share with us those fields. I believe that with the backgrounds we have gone through a few sessions and this forum is familiar with.
Mm-hmm. Okay, I can skip to.
Just 1 second. It would be great. It would be good if you can still like go through it, but let's say a little bit quicker. But because I want to have
Mhm.
this video on its own also, like self-explanatory rather than like with references and so on. But like
Oh,
let's go
Okay.
like let's not skip it, but just
okay.
let's go faster through it.
Okay, yeah, so in a sample PTP network, we have a grandmaster clock that is synchronized to a GPS source. We have a boundary clock and a couple subordinate clocks that are synchronized to the boundary clock and to the grandmaster through it. I will not introduce the protocol itself then. I will just quickly skip through this slide. And if it comes to the timing of the timestamp, in the ideal world, we would timestamp and transmit the packet at the exact same point in time. Obviously, in the real world, there is always some kind of error that results from the fact that we are timestamping the packet earlier than we can transmit it. And we have either software timestamping, which is we are reading the system clock, saving the timestamp, then pushing the packet into the stack, waiting for it to be transmitted. That leads to having a quite significant error. That's why we have the hardware timestamping, which actually requires us to set the appropriate flags in the descriptor and then push the packet to the hardware, and the hardware will generate the timestamp when it just before it transmits it, and then it will transmit it. This gives us relatively small error of the timestamping. Okay,
Can you
so now
specify which NIC are you referring to?
most of Intel NICs supports this. The ones that supports the hardware timestamping actually does that. They can generate the timestamp when the packet is sent and when the packet is received.
That's the 700 series, the 800, both?
Both.
Okay, thank you.
Yeah. Okay, so now let's move on to the kernel interfaces. Basically, let's start from the bottom. In hardware, we usually implement some data queues and the additional PHC clock. The PHC clock is the source of the hardware timestamps. On some NICs, we also expose the external pin interface that can do something with the PHC clock, so it can enable synchronization of this PHC clock to either external 1PPS clock, or it actually can become the 1PPS source for other devices. Then our NIC is obviously connected to the PCI bus. The NIC driver has the access to both queues and the hardware clock through the PCI. It exposes the PTP clock as a POSIX clock inside the kernel, and it exposes the transmit receive queues for the network stack with additional socket options to configure the hardware timestamping. And also the PTP clock has its own set of the IO calls that can be also used to change its parameters. And finally, we have the user space in which we run the IEEE 1588 protocol inside that is implemented inside the tools in the Linux PTP project. The Linux PTP project itself uses those kernel APIs mentioned before to actually interface with the PHC and with our NIC and hardware timestamping logic. And finally, the sysclock is symbolically drawn in the user space here because getting time from the sysclock does not really hook to the kernel, so it's the fastest source of time in the user space that is strongly recommended to be used in the applications. Okay, moving on to the Linux kernel, we have the interface for the external synchronization pins. We have actually those three interfaces that I mentioned before. We have one interface that is used for configuring the external synchronization pins. This is the standard sysfs interface. It supports either external timestamping input, so 1 PPS input, and the periodic output, which we use as 1 PPS output. We have the socket options that control hardware timestamping and actually are the way where we receive the timestamps that were generated by the hardware. And we have the POSIX clock. Just a second, I need to move the window. And we have the POSIX clock that actually exposes the POSIX clock's APIs and the IO calls to it. If it comes to the PTP pins interface, they are under sysclass PTP and the PTPX, which is 4 in this example. In the pins subdirectory, those files represent all the physical pins that we expose from our card that can be used to somehow interact with the PHC clock. And those pins are configured in the way that you need to echo the function followed by the channel into this file. And the functions could be either 0 for no function, 1 for external time source, which is the input, and 2 for periodic output, which is the output. More details on that can be found in the documentation. And the other important files in this subdirectory are the extts_enable. This file is used to enable the external time source synchronization. So we need to echo the channel followed by number 1 to enable or 0 to disable this feature. When you do that, the PHC will start synchronizing to the external timestamping source, which is usually a 1 PPS signal coming from the GPS. And if you want to use our card as a 1 PPS source, you can echo the channel index followed by, in our NICs, we don't support all those features. But if you follow it by 4 once and echo that into the period file, you will enable 1 PPS output from the card. And more details can be found in the documentation. So another interface is the POSIX clocks API. All the clocks are represented as character devices in the dev subdirectory. The clocks can be adjusted by calling the clock adjust time function, and there are this function actually calls into 2 separate hooks in the driver. It's either adjust frequency or adjust time. Adjust time is non-monotonic, so it will create a jump in the time. and adjust frequency or adjust fine. We'll try to adjust the frequency at which the PHC timer ticks to actually match the time between the source and the subordinate, between the master and the subordinate. And obviously there is a function to read the time, which is clock get time, and to set the time. And there is a bunch of optional IO call methods that this clock supports, which I'm not discussing, but there is a link to the documentation on the previous slides. If tool. If it comes to this tool, you can use it to easily check whether your hardware actually supports hardware timestamping or not. If you want the hardware timestamping, you should look for those lines. Sorry, there is one mismatch, but this should be the hardware receive, hardware roll clock, and hardware transmit. And yeah, that sums up the introduction of the Linux interfaces, the standard ones. Are there any questions?
One question.
Yeah.
The external timestamping, where is that happening? Like, is that I mean, can you show that in the diagrams, like where specifically that happens, like in the combination of like that's a hardware and software kernel, like?
External timestamping is the use of the external pins that are attached to our NIC, exposed by our NIC, and those pins can be used to actually synchronize our PHC clock to the external time source.
No, I know the mechanism, like taking a snapshot. So the snapshot happens basically, do you have like a parallel, let's say, register to what the PHC is, and then this gets copied there, like let's say an array of, say, I don't know, whatever.
If I remember correctly, this is used to generate the events in the system which could be received, and we get the timestamp of this event with this event.
So do we use like the same mechanism that is used to do stamping for packets when they come in and out, or something like that?
Not really. I mean, the logic behind it is pretty similar, but it's a different piece of kernel, because this is part of the clock, not of the NIC.
And then it gets handed to the kernel, and then the kernel basically provides it to you. Is that something like that?
Yes, if I remember correctly, then yes.
Okay. Thank you.
There was a question.
Sorry, I failed to understand. So that means that we can use software servo to discipline using the external timestamp?
No, we can use the hardware servo, and it will capture the when there is a raising edge on the pin, it will capture the time when it arrived, and then we can use this timestamp to actually correct the PHC clock, just like we can do with the
Okay, thank you.
When you adjust the frequency of the PHC, is that something you do like every second, or is it based on the oscillator on board?
It's configurable. The tool that runs, we can maybe come back to that later when we are talking about the tools. I can explain it there if that's okay with you.
Sure, thanks.
Okay, so let's move on to the tools introduction. The toolset that we are running with is Linux PTP. It's a set of user space user space tools that implements many PTP functionality. It's maintained by Richard Corhan, who is actually also maintaining the PTP subsystem in the Linux kernel. It implements the IEEE 1588, uses standard kernel APIs to manage the PHC clock and correct it and do everything that the toolset can do, which I will explore in those slides later using the standard kernel APIs. And it supports both hardware and software timestamping, but obviously we want to focus on the hardware ones. And you can find the latest version of it on the SourceForge. I strongly recommend getting it from there, because usually the distributions have older versions of this package. And for example, in the latest one, they added a new very useful tool, which I will introduce a little bit later. So there is the Linux PTP toolchain consists of 4 main tools. The first one is PTP4L. This is the tool that provides the implementation of the IEEE 1588 protocol. And this can be used to synchronize 2 PHCs using the PTP. TS2PHC is the latest tool in the toolchain. It is used to synchronize the PHC clock to the external 1 PPS signal, the hardware one that I mentioned before. The PHC2sys is the tool that gives the ability to synchronize 2 or more POSIX clocks. Can synchronize, for example, PHC with the system clock or the other way around.
Wait, so earlier you said that the external timestamping cannot be disciplined by a software servo. This tool is actually a software servo. So do you support
external timestamping? But you mean the PHC clock?
No, the PPS in. I mean, the TS2PHC allow you to take a PPS in and discipline your PHC with that.
Yes, that's true.
So the Intel NIC supports that?
Yes.
Okay.
So
you do allow software servo to be disciplined by that.
But by software servo, you mean the servo that corrects the hardware clock, or what do you mean by the servo?
Servo is a control mechanism that filter outliers and doing a PID.
Yes.
That's what I mean.
Then yes. Then the answer is yes, we can do this, because we can generate the events for every incoming PPS.
Okay, thanks.
Okay, yeah, so that was the PHC2sys, and the last tool in this set is the PMC, which is PTP Management Client. This is the tool that can be used to pull some useful information from the running PTP4L tool. So as I previously mentioned, the PTP4L tool is the user space app that implements IEEE 1588 protocol. It can be used to synchronize the PHCs running on our NIC to the hardware, to the master clock, or actually serve the master clock to other systems in our network. Can be run either as a standalone tool or as a service, and uses the PI servo to actually adjust the frequency of the PHC. And you can find more details on this tool in the manual. And if we want to run this tool, this is the helpful guide of how to do it in the very basic setup. On the master system, you need to run the PTP4L, and I will explain the parameters now. So -I parameter gives us the network interface to use. So this will specify the port that it's running on. -M will print the messages to the standard outputs when we want to print the messages to the console instead of the DMESC. -F will read the config file specified as a parameter, and -S will enable the slave-only mode. So on the subordinate system, we will want to specify that if we don't want the system to become a master. So when we run it on the master system, the tool will initialize and start listening for packets, select the local PHC as the master clock, and when you see assuming the grandmaster role, this system actually becomes a grandmaster. And on the other end, when you start the tool will actually initialize. It will try to find the master in the system, and then it will start synchronizing the PHC. And once it runs for a while, it will show you the following output. In this column, you can see the offset to the master clock expressed in nanoseconds. Second column is the synchronization state. S0 means that the servos are totally unlocked, so the clocks are not synchronized. S1 means the clock step, which is the non-monotonous step, so we need a bigger adjustment than the maximum allowed by the frequency change. S2 means that the servos are locked and we are actually using only the frequency corrections in the synchronization whenever it's obviously possible. This shows the frequency difference to the master clock. And now we can come back to the frequency question. Basically, this is the parts per billion of the frequency that the clock sticks on, which means that the corrections here are rather slight. So we are working on the sub-nanosecond corrections. And this shows the delay of the path between the master and subordinate system. Okay, second tool is the TS2 PHC. This is the newest tool in the package. It was added in the Linux PTP 3.0 and may not be available in the distribution packages. This tool is used to...
If I may, before you go to the TS2 PHC, on the PTP4L, you showed something relatively simple between a point-to-point, like one master and one subordinate. Any opinion on when you want to implement a boundary clock, let's say with, for instance, one subordinate port and multiple master ports, let's say 36 master ports. How there's not a whole lot of literature on how to configure, such, what I just said in my example. Let alone, there's not a whole lot of literature about the best master clock algorithm or any kind of alternate best master clock algorithm. Any experience on this you could share?
But you mean like having multiple NICs serving the time to add to different parts of the network? Is that this kind of boundary clock?
Could be multiple NICs in one network element, could be one giant NIC in one network element where you have, multiple ports, let's say 16, 32 ports, for instance, where one port is going to be a subordinate and all of the other ones are going to be, a master. Essentially implementing a boundary clock, not just a point-to-point like you just showed in your example.
There is one option mentioned later in the deck. This includes running the master on two NICs and using the external 1 PPS signal as the synchronization method between them. If that helps.
Maybe we can progress, but I think my question was more about the JBOD option that exists, just a bunch of devices in the PTP4L stack, and wondering if because there's not a whole lot of information on how that works, how to configure it, how stable it is, and so on. But we can proceed, yeah.
Okay, yeah, I don't have experience with that kind of scale. Maybe Ahmad will have some.
Okay, thanks.
Yeah, like So like I make we can work with Michelle on this. Like we have to experiment a lot with these things. Unfortunately, the documentation is pretty poor on this, but and like hopefully we can again. Documentation is something for this kind of open source thing is literally the community effort. So we can all work together and make things like basically document our findings. Let's proceed.
Okay, yeah, that's always useful to, do the feedback loop to the documentation. Okay, so let's go back to the presentation. The TS2 PHC tool can be used to synchronize the PHC to the incoming 1PPS signal. And in the latest version, it can use the NMEA GPS input to the serial port as the time value, and then by using it with the 1PPS, we can easily deploy the Grandmaster using this tool. And obviously, there is a friendly manual on that as well. So if we want to run the TS2 PHC tool, we can specify the config file by specifying the -f parameter. -s will specify the source of the PPS signal. Generic is used for the external 1PPS signal. We can use the master PHC clock that is generating the PPS events, and NMEA for GPS. -m will print the log messages to the standard output, and -c will specify a PHC subordinate clock that will get synchronized in the process. It could be either the character device or the network interface. And this tool
maybe it's worth it to mention here that like when you go back to the generic, the options you have on generic, you have now the ability to take one PHC and put it on the other one. Basically, TS to PHC is taking over PHC to sys.
Yeah. But the PHC needs to generate the PPS events, right?
Yeah.
Okay, so
the PPS dictates the frequency, and the NMEA dictates the phase, right?
NMEA gives a TOD.
NMEA holds the
TOD.
timestamp, actually, the value of the time.
Yes.
Because NMEA word, the general minimum required message has the time, the actual time.
The sentence GPGGA has basically the time.
Yeah.
And does the PTP Linux PTP support several NMEA formats or just one?
No, it only supports this one, the GP recommended minimum message.
Yeah. So the GPRMC has basically about 5 or 6 different sentences. One of them is the one that includes the time, and that's the only one that gets basically filtered.
Okay, so now let's move on to the PHC to sys. This tool is used to synchronize the system clock to the PHC running on the NIC when the NIC is synchronized to the Grandmaster or other master. It can work both ways, so it can both synchronize the system clock to the PHC clock, but it can also synchronize the PHC to the system clock if that's what we require. The tool can run either as a standalone tool or as a service, and there is the link to the manual to that tool. And the command line of it is the following. -s will specify the master clock. You can use device interface or the name of the clock, like clock real time for the system clock. -c will specify the subordinate clock. The same applies here, so you can specify device interface or the name. -W will force the tool to wait for the PTP4L synchronization. So when the PTP4L is in sync with the master clock, then the PHC2sys will start actually applying the correction to the system timer, and -M will print the messages to the output.
One thing, Masic, I don't know why, you have to basically put -W. If you don't put -W, it doesn't work. And there
Yes, because you then need to specify the offset between the clocks. I think it's -O with 0 will give you the
-0, yeah, offset 0. That's right.
yeah. And yeah, we have the output of the PHC2sys that's running. Similarly to the PTP4L, it prints the offset to the master clock, prints the state of the synchronization, the frequency difference to the master clock, and the delay of the path. And the last tool we will talk about today is the PMC. This is the PTP management client. This tool can be used to obtain some information from a running PTP4L. It accepts a lot of messages, so the best place to check which one can it pull is the manual. And the example command line is explained here. So -U will use the UDS local, which is the local link to the PTP4L running on the same system. -B will specify the number of boundary clocks. So 0 will read the status of our side. The 1 will go deeper in the chain and will also pull the stats from the master. And this parameter will actually read the port statistics, so it will give you the nice info of how many packets were transmitted. And now to show this, to put all the tools together and show how they fit into the system. On the Grandmaster clock, we can use the TS to PHC to synchronize to our GPS receiver connected to our SMA inputs. Then we can use PTP4L on the master side and on the subordinate side to synchronize this clock running on this NIC, this PHC actually running on this NIC to the Grandmaster. Then if we want to scale up the boundary clock and add more NICs that will be synchronized to this PHC, we can use again the TS to PHC and configure this NIC to generate one PPS signal and this NIC to receive this one PPS signal. Then run the PTP4L again on this side to serve as a master for the subordinate system, and run the PTP4L on the subordinate system to synchronize this PHC to that one. And in the end, if we want to also synchronize the system clock, we can use the PHC to sys to actually synchronize the PHC to the system, the system clock to the PHC that was earlier synchronized to our boundary clock. And if we do that, we can just read the system clock to get the accurate time. And if it comes to command lines, on the master system, we first need to configure the pins. This is, for example, configures one of the SMAs as the external timestamp input. Then we need to enable external timestamping. After this, we can run the TS to PHC to actually synchronize to those timestamps. Then we will start the PTP4L as a master on that same interface. And then on the subordinate, we can run the PTP4L and run it as the subordinate system. It will start synchronizing to the Grandmaster. And in the end, we will run the PHC2sys to actually synchronize our system timer to the timer running on the NIC. Yeah, and that sums up the presentation. So thanks for your attention. If you have any questions, we can discuss.
Any plan to support Sync E?
I can't answer this kind of questions here, right?
So one question, Message. Do you have experience with running the TC with PTP4L?
TC, you mean what by TC?
Like basically, like if you go back to that slide where you have like you're showing like from like making the grandmaster all the way going to basically to the system clock. No, that was good. Like
Network
yeah.
slide.
Come forward. Yeah.
Okay.
Yeah, this
Yeah.
one. Yeah, like see like where you have the boundary clock. Let's say if you wanna test transparent clock, because transparent clock is also something you can run on PTP4L. Unfortunately, it's not for let's say unicast. And let's say, for example, if you have you make the routing basically from one port to the other, so you can basically have on the same network, like you basically can have grandmaster pinging directly, let's say the subordinate. So now you're instead of a boundary clock, you want to put a transparent clock. Do you have any experience with that? Like I never tested this.
Not really. I know that PTP4L supports the transparent clock mode, but I never really used it, so I can't really relate to that
Yeah,
too
again,
much.
due to the poor documentation, really poor documentation, specifically on a transparent clock, I only found out that transparent clock can work probably if it is going to work. It will work only on multicast and not unicast. Like it cannot intercept packets and basically put correction field or something. So that's what
Yeah,
I observed.
that's possible. This is probably a software implementation that would need to be changed there.
Yeah, and another problem that I faced with basically making the boundary clock, let's say in the case of you have two ports, most of NICs, like the two ports with one PHC instead of two PHCs, then you don't need basically the TS2 PHC. The thing that we face is like if you want to run the boundary clock with the way that it was advised, like basically like you have let's say both like ports there and you define like which one should go basically upstream, downstream, and so on. We figured out that if you run two separate PTP4L instances, one acting as a master, one acting as a subordinate, subordinate basically facing the master, and the other one acting as a master and facing down, it works more stable than having them in one, basically doing both. I don't know why.
Okay, yeah, that's interesting input.
I think that was a bit the question. Thanks for bringing that up, Ahmad. The same question I had is in this case of the boundary clock here, you show one subordinate, one master. That's fine. But what if you want to enable, multiple paths through a boundary clock, or you want to have redundancy where you might have one subordinate, one port that is in passive, use, let's say, for redundancy, and multiple ones that are in master. It's very, very unclear whether this is possible with PTP4L, let alone how to even configure that. Yeah.
Good that you brought it up. There is also another problem with the when you go on you want to do unicast. You have I forgot the switch. There's a switch, something set to 0. If you add that one, I think it's called listen unicast or so, listen only unicast or something.
You mean
Yeah.
the unicast flag in the packet?
Yeah, if you set that one, like basically you wanna force basically unicast, right? So if you set that one up, you will have a problem of timing out. Let's say for whatever reason, if you're the client doesn't talk to the grandmaster on time, like the subordinate, the grandmaster will basically fail, like basic on the master thread. But then if you take that one off, you will have a very robust grandmaster. But then checking it with the tools, I realized that your grandmaster starts basically sending you like multicast messages as well. So
Mm.
there's something wrong here. Like basically the timeout thing is tied to the unicast.
Okay, that's interesting.
Ahmed, relating to what you were mentioning earlier on the TC, how is the correction field supposed to be updated? Normal, I mean, ideally it will be done by hardware as well, but I'm just not sure if the NICs, the final NICs can update the correction field or only the.
It will be it will be like a two step mechanism. So you send it and then there will be a follow-up going after, hey, he was here, like, I don't know, packet was here.
Okay, so it's not going to be, so trying to do that with one step is a problem.
Yeah, it's a problem because in one step the packet is sitting there, timer finishes like the egress, and then there's a prediction. It has to be hardware, right? It's a prediction that it's gonna take that much in the future. So add that one to the correction field, right? But you don't have that, so only two step. And that make I don't think anyone else experimented with that here. But as far as I know, it only works in again multicast. In multicast goes with two step, and the servo accepts two step. And for the two step, it has also a timeout. It waits for the thing, doesn't come, it assumes that was the last. And you can imagine if you have, let's say, multiple transparent clock hops. Oh, now
it's a multicast storm.
It will be a swarm of messages going back and forth because each one of them will trigger like two more, four. It just goes crazy. Like unless you have them like just going without like time sensitive, which they don't need to be time sensitive because they just include a time, but they have to go fast. They have to have priority.
Yeah.
And just to add on this, because I think we discussed that a bit a couple of weeks ago during the profile, that if you use a transparent clock in two-step, a lot of the data centers use what we call packet spraying type of techniques to basically balance the load between, the forward path and the reverse path, right? Both directions. And this is where a two-step transparent clock breaks. Because in order to, if you look at 1588, it's very clearly spelled out that in order to support a two-step transparent clock end-to-end, operating in end-to-end mode, you need to make sure that the sync message, as well as the delay response, the delay request and the delay response follow the same path. Or else there's absolutely no way to update, in a two-step, it's the delay response that is being, updated. If it so happens that it follows another path between point A and point B, you're going to be the delay request, response mechanism is going to be measuring something different than what it's supposed to measure. So these are the kind of things that are interesting also to discuss at one point.
Yeah, to me, it seems like adding transparent clock, like the ability to make transparent clock with PTP4L, was more for the sake of completeness, like obsession of like, okay, let's have everything implemented on this tool. But in like practically
Checkbox was
speaking,
checked.
yeah, exactly, yeah. But like just get everything checked, basically, exactly. But like practically speaking, I don't see like that much of a use for it. And like I don't know, I think we discussed this in this forum also. Like we are thinking about a new, which is not a new thing. It's basically the master clock or like / boundary clock that is going to be in unicast system for scalability. Can basically apply the both like basically communicate with the grandmaster and like the subordinates on the same port. So this is, let's say, when you want to scale for a very fat clock tree, which you have, let's say, assuming, let's say, you have like 5,000 switches. Each switch has like, let's say, sorry, 5,000 racks. Each rack has, let's say, 50 to 200 machines, and then you have, let's say, one grandmaster. So practically speaking, 200,000 to 1 million machines, which is the total, cannot talk to directly to the grandmaster. So you need some sort of hierarchy. And let's say boundary clock is one option, but if boundary clock is not available because it takes like time for deployment and changing in the infrastructure and so on, you just enable transparent clock, which is relatively trivial because it's just provided by the ASIC. And then you have now one machine per rack, per every rack, one machine only, that is going to talk to the grandmaster. Every other machine in that rack talks to that machine. So like basically, like we calling it designated master clock. It's basically.
Sorry, a transparent, an end-to-end transparent clock does not take part in the PTP session, so that it essentially, as any slave or any subordinate within the rack would be talking directly to the grandmaster or to the next available master, whether it's a grandmaster or a boundary clock.
Because this is unicast, the direction is determined by the IPs, the IP addresses, right? So all the infrastructure is acting transparent clock, meaning all the packets will face like with the compensation of the correction field. They will feel as if there is no any delay, so they can just work freely, right? So you have these packets from one machine basically in this, let's say, rack, talking to the grandmaster. Every other machine talks to this machine again via the same switch. Yeah. You're basically moving the servo from the, let's say, in this rack, which like in the first architecture, you had the rack, you had the boundary clock on top of the rack. You move the boundary clock, the servo part of the boundary clock, basically, off to one of the machines. So it's just a good way, basically, to pave the road. I'm not saying it's an elegant one, but it's a good way to pave the road while, let's say, your infrastructure is getting ready for like a full-blown like a structure where you have boundary clocks and so on.
Right. Gotcha.
Intermediate solution, I'll say.
Yeah.
Okay, Elad, what do we have on the agenda for the next?
So
5
before
minutes?
that, I had another follow-up question on the sync key. So maybe to everyone here in the forum, do you guys see the need to have sync key implementation as part of the Linux BTP library? Is that some kind of a need that?
I would say the main benefit would be holdover, if possible. Even though it will generate better PTP performance and even simplify the disciplining and servo, but considering the fact that we're getting pretty decent performance related to our performance timer or target, the main benefit would be holdover. But it could be tricky if we start walking through chains and we're looking into redundancy and multiple paths of sync E. That needs to be implemented pretty carefully.
Yeah, I think sync E in our application, like you have sync E as long as you have the connection. And if you have the connection, again, it really depends on the scenarios. Like I'd say I can see how in telecom sync E is like a must. But in our case, like let's say if we don't have the connection, if we lose the connection, we have a more serious problem to deal with than time. So because like our nodes are sitting, they communicate with the outside world via the network. While in telecom, you have the MBH, but then you have like the clients are sitting basically at the end of these like let's say the end nodes. So I don't know, like I need to think more about it, like with regard to Syncy. But like let's say for message, like again from PTP4L, I don't think we have anything like in kind of support or something for Syncy, right? Server wise or anything.
No.
I think it's also a question of the NIC itself. It needs to use the recovered clock for that purpose.
Yeah, There's sync E, CPRE, like CPRE, a lot of things. Like Dotan, is there anything like from your end like you want to add to this?
We definitely understand the need. That's no question.
Mhm.
What Shamir said is I second everything that Shamir said,
Mhm.
and I would love to see that in Linux PTP.
So do you guys have already an internal tool or something? Like, I don't know, whatever you can discuss, like for the sync E that we can, like Linux based, that we can, let's say, push
No.
forward, let's say, to the open community? No, not yet. Okay. We can probably look into that then.
Okay, thank you. With the remainder of the few minutes here we have, I guess only time for messages. So the next meeting is happening in 2 weeks, and we have Hisham from Nortel who volunteered to have a session. Hisham, what will be the subject? Hisham? Okay.
Yes, I'm here. Yes, I will present it next week.
In 2
Next
weeks'
week.
time. Yeah.
Hisham, any sneak peek? Like what would the topic be about?
I will just describe time-sensitive networking and its applications and how IEEE 802.1 and .1 Rev, which really provides a profile for BTP for time-sensitive networking. Like, for example, using time synchronization in a factory or industrial Ethernet or automotive applications. And
Thank
you
you.
can also use it for data center if you're running time sensitive applications in data center. You can use it in edge computing if the edge would like to run an application which require time synchronization. This can also apply. That .1 Rev can apply.
Looking forward to hear more on that. Thank you very much for stepping in. And then in 3 weeks' time, so that is November 12th, we will have the TAP day in the overall OCP Tech Week. So the whole week will be full of sessions and tracks. The TAP track is happening November 12th, and we look forward to have everyone there. The agenda is available on the website, the OCP Tech website. And if you have any comments or feedback, please share it with us all. Thank you very much. Closing off the
Thank you
call.
all.
Thank you.
Thank you.
Thanks.
Bye,
Thanks,
everyone.
Bye.
Bye.
Thanks, bye.
This conference will now